At what angle of incidence will sunlight reflected from water be completely polarized? Okay, so here we are going to assume that n equals 1.33, which is the refractive index of water. Now, for sunlight, we can also assume that this is unpolarized light. Okay, so here the angle of incidence, if it's going to be completely polarized, this is telling us that it is Brewster's angle. Therefore, we can use the formula theta b, Brewster's angle, equals the inverse tan of n2 divided by n1. Now, in this case, n1 is 1 because it's air. Therefore, this is going to be inverse tan of 1.33 because it'll be 1.33 divided by 1. And then when we do that, we get basically exactly 53.06 degrees, which is roughly 53.1 degrees. And that's the answer to part A. Part B. Calculate the upper and lower limit of the Brewster angle for white light incident on fused quartz. Assume that the wavelength limits of the light are 400 and 700 nanometers. Okay, cool. So we have two wavelengths of light. For violet, it's 400 nanometers, and for red, it is 700 nanometers. And the relationship between refractive index and wavelength of light is shown below. Okay, so we have two wavelengths of light. We have 400 nanometers, which is going to equate, or I guess equal or correspond to a refractive index for violet light through fused quartz of 1.47. Then for 700 nanometers, this is going to correspond to an index of refraction through fused quartz of 1.455. Okay. So we need an upper limit and a lower limit of the Brewster angle. All right, so we have two values of our refractive index. We have our equation here, theta b equals the inverse tan of n2 divided by n1. Now, we are going to assume that n1 equals 1.00 again. Therefore, let's work out the Brewster angle for violet light. That's going to be inverse tan of n, which is going to be the 1.470. And when we do that, I get 55.77 degrees, or roughly 55.8 degrees. And then for red, the refractive index is going to be the 1.455. And then when I do that, I get 55.5 degrees. Therefore, the lower limit is 0.5 degrees. The upper limit is the 55.8 degrees. Okay, cool. That's the answer to part B. Part C. A light ray is incident on a flat layer of material 2 that has an index of refraction of 1.5. Beneath material 2 is material 3 with an index of refraction n3. The incident ray on the air material interface, material 2 interface at the Brewster angle. Is at the Brewster angle for that interface. Okay. The ray of light refracted into material 3 happens to be incident on the material 2-3 interface at the Brewster angle. Okay, so I'm just going to draw what's happening, and I'm just going to do it up here to give myself some space. So what we have is we have a couple of materials. We have material 1, material 2, material 3, and then we have light coming in incident here. Now this here is the Brewster angle for material 1, 2, and this is air, I believe. Yep. So this has a refractive index of 1, material 2 is a refractive index of 1.5, material 3, we don't know what it is. Okay. So this then refracts at some angle. So when this reflects, this happens to be a right angle here. And then this then refracts somehow. And the reflection, this here happens to also be 90 degrees because this is the Brewster angle for the second and third material interface. Okay, so there's a couple of ways in which we can do this. I'm going to do it the long way first, and then I'm going to do it the short way second. So the way that you can do this is you can literally step it through one by one. Okay, so the Brewster angle for the material 1,2 interface is going to be given to us by the inverse tan of N2 divided by N1. Therefore, we can work out what this Brewster angle is going to be. Now, N1 in this case is 1 and N2 is 1.5. So when we do that, I get 56.3 degrees. Okay, so 56.3 degrees is this angle here, which happens to be this angle here. Okay, so the way that we can work out, we know what the refractive index of the first and the second materials are, and we know what the incident angle is. Therefore, we can use Snell's law. N1 sine theta 1 equals N2 sine theta 2 to work out what the refracted angle is, this one here. So to work that out, which is going to be this theta 1 is going to be theta, the Brewster angle of material 1 and 2. Okay, so this is going to be sine of our 56.3 degrees is going to equal 1.5 sine of the refracted angle. Okay, so the refracted angle is going to equal the inverse sine of 56.3 degrees divided by 1.5. And when we do that, I get 33.69 degrees. Okay, now, interestingly, if we sort of work out these angles, the Brewster angle happens to be the refracted angle for this angle that we just calculated. So therefore, the Brewster angle for material 2,3 is 33.69 degrees. So therefore, we can use our equation. So we're going to say tan theta Brewster angle of 2,3 is going to equal N3 divided by N2. So therefore we can say 1.5, this is N2, times tan of 33.69 degrees is going to equal N3. Now for N3, I get roughly 0.998 or 9998 the refractive index, which is roughly equal to 1. So we can say that material 3 is air. Okay, so that's the long way of doing it. There is a shorter way of doing it, and it's by doing a bit of algebra to begin with. Okay, so let's actually just do that. So I'm just going to do it here. Okay, so you might be thinking that you want to do it a slightly shorter way. Okay, so we're going to have a couple of equations here, right? We're going to have tan theta of the Brewster angle 1, 2 is going to equal N2 divided by N1. That's equation 1. Equation 2 is going to be tan theta of the Brewster angle between material 2 and 3. And that's going to equal N3 divided by N2. That's equation 2. So what we are going to do is we're going to go equation 1 multiplied by equation 2. So we can see we've got N3 divided by N2, N2 divided by N1. We're going to be able to cancel out N2s here. Okay, so let's actually do that. We're going to end up with N2 divided by N1 multiplied by N3 divided by N2. And that is going to equal tan theta of Brewster angle 1, 2, tan theta Brewster angle 2, 3. Okay, so we are going to try and work out what our angles are here. Okay, so if this is the Brewster angle of material 1 and 2, and this is the refracted angle, which happens to be the Brewster angle of 2 between materials 2 and 3, what we can say is that the Brewster angle between 1 and 2 plus the Brewster angle between 2 and 3 equals, or plus 90 equals 180, but these two added together must equal 90 degrees. Now, this is really useful because what we can say then is that the Brewster angle of, say, 1, 2 is 90 degrees minus theta of the Brewster angle 2, 3. Okay, so what we can do is we can cancel these and we can say, well, N1 equals 1. So we can say N3 equals 10. Now let's actually sub this in. 10 of 90 degrees minus the Brewster angle between materials 2 and 3. 10, the Brewster angle between materials 2 and 3. Okay. Now, here we need to do a trigonometry identity, and the identity that we're going to use is tan 90 minus theta equals 1 divided by tan theta. Now, this also happens to equal cot theta, but this part is the bit that we're going to use. So you can see if you just move the tan to the bottom, get rid of the 90, it all works out. So we're going to do the same thing here with this thing. So we're going to end up with N3 equals tan theta, Brewster angle between 2 and 3, divided by, now remember, get rid of the 90, move this to the bottom, tan theta of the Brewster angle between 2 and 3. You can see these two cancel, so we're left with N3 equals 1. So that's a slightly quicker way of doing it. And that's how we do this question.